Today we're going to talk about another hypothesis of Galileo. Galileo famously hypothesized that object projected horizontally will reach the ground at the same time object dropped vertically. What am I talking about? Let's write down Galileo's hypothesis. Object projected horizontally reach the ground at the same time object dropped vertically. Alright, so what is Galileo talking about? 1590. What is Galileo talking about? 1590, some 400 years ago, 26-year-old Galileo. What is he talking about? So let me explain what is he talking about. Then first graphically, and then I'm going to give you an example. Alright, so object projected horizontally. Let's draw object projected horizontally. So let's put in a let's make a table. Object. So pay attention to this because this is very important. Object roll horizontally. So there is a ball. The ball roll horizontally with velocity, I don't know, roll horizontally with velocity 5 meters per second, or 10 meters per second, or 20 meters per second, 100 meters per second, doesn't matter. So object roll horizontally with some velocity. Alright, so object roll horizontally. So this object roll horizontally with some velocity 10 meters per second. Alright, what happened with the object? Object eventually come. This is the edge of the table, and then the object falls and eventually hit the ground. Object eventually hit the ground, and object eventually here. All right, at the ground, landing on the ground. Okay, now what is happening right here, right over here? So this is very important. Right over here, so edge of the table is very important. So at the edge of the table, the velocity has two components. So the velocity has two components, Vx and Vy. So Vx, so object roll horizontally means that Vx is 10 meters per second. Whatever Vy is 0 meters per second. Alright, so Vy is 0 meters per second. By definition. So this is why Galileo is saying that this is the same as object drop. So what happens if you drop an object from, this is 20 meters, the table is 20 meters. What happens when you drop an object from 20 meters above the ground? So this is you are on 20 meters above the ground. You are standing over here. And you drop an object. All right. So you are standing over here from here to here. So this is the ground. So from here to here is from here to here is 20 meters. So from here to here is 20 meters. So you are standing somewhere on the somewhere there. So you drop it, so it's also 20 meters. So you drop the what? You drop the ball. So you drop the ball. Alright, so from 20 meters above the ground. So the Galileo is saying that they're the same. That means if this takes t time, this also takes t time. Alright, let's prove that. But before I prove that, I'm going to prove that this will take the same amount of time as this, because 1590, 26-year-old Galileo says so. So I cannot say something else in 2020 because he was a smart dude. Alright, so before I do that, I want to show you what's going on over here, and that is the first x component of the velocity. That's what I'm going to show you. The x component of the velocity. Now I'm going to erase this for a second. So first I'm going to show you the x component of the velocity. So this is Vx. I'm going to choose only 3 or 4 points. So Vx is Vx. This is also Vx. And this is also Vx. So Vx is 10 meter per second, Vx is 10 meter per second, and Vx is 10 meter per second. Alright, so what do you notice? You notice that Vx at the x direction, velocity at the x direction is constant because acceleration due to gravity at the x direction is 0. Alright, what happened at the y direction? Let's take a look. At the y direction, at point 1, alright, I'm gonna put more arrows. This is because I need them. Even if I put more arrow, they're all gonna be the same. They're all gonna be the same. 10 meter per second, 10 meter per second. All right, now I'm going to do red. To see, the green is the x component of the velocity, which is constant 10 meter per second because acceleration due to gravity at the x direction is 0. So velocity at the x direction is constant. It's constant. It's not going to change because acceleration due to gravity at the x direction is 0. Alright, now what I'm going to do, I'm going to show you the acceleration due to gravity, how acceleration due to gravity affect velocity at the y direction. So the velocity at the y direction is equal to 0, so I'm not going to put anything over here. So then is increases and is increases. So this is Vy. This right here, Vy is 0. That's why I didn't put anything. So this is Vy, this is Vy, and this is Vy. Alright, so now, I'm going to show you the time. So how long does it take? So now let's find the time. So in order to find the time, you can use the d is equal to Vit plus half at squared. By the way, you have to use the y direction one. Alright, so the dy is negative 20. Negative 20 is equal to minus 5t squared. So negative cancel. Say 5 goes to 24. So t squared is equal to 4. So t is equal to 2. So it's 2 seconds. Alright, so how long it takes for the ball to hit the ground? 2 seconds. Now I'm going to show you that this will exactly take 2 seconds because 1590 Galileo said the horizontal projected motion is equal to the object draft vertically, and they will take both at the same time. Alright, now let's find the time. So this t, that t is 2 seconds. 2 seconds. That one is 2 seconds. Now let's see this one. Alright, so how long it is? 20 meters. So d is equal to Vat plus half at squared. Now what is the v initial when you drop the ball? Of course 0. Alright, so d is negative 20 meters is equal to half negative 10 t squared. So negative 20 is equal to negative 5t squared. So t is equal to 2. So 2 seconds. Alright, so yeah, Galileo was right. Object rolled horizontally, no matter how much velocity, it could be 10 meters per second, or it could be more. It doesn't matter, or it could be less. So object rolled horizontally with 10 meters per second takes exactly the same time to fall when you drop the object from the same height. Thank you, Galileo, for expanding our understanding some 400 years ago. We are still using it today.